and so welcome to our webinar on forces, and in particular we're going to talk about resultant forces and streamlining. So I need to remind you a few things about forces. So you've probably done a little bit on forces in year 7. We've talked about forces being a push and a pull, and forces being able to change the shape of an object or make it accelerate or decelerate or move. And hopefully you all know that forces are measured in newtons. So here are some forces. We have a standard push, just a straightforward push force. We've got tension force when you are stretching something. We have magnetic force. Those are the field lines around a magnet, and we've studied magnets, so we know all about magnetic field lines and magnetic force. We've got here what's called a normal reaction force. So that is when we put a weight on top of something, it's the force back up from that object to stop it from falling. So you're standing, maybe sitting on a chair now, and the reason you're not falling on the floor is the chair is giving you a normal force back up to prevent gravity from sitting you on the floor. We've got gravity there, air resistance, and electrostatic force. And I know that some of you know about electrostatic forces and ions and atoms, and that is the same electrostatic force that we're talking about. So which of them are non-contact? Non-contact means forces where the two things don't have to touch each other for the force to still exist. Well, a push quite clearly is a contact force. Not actually touching the object, you can't push it. Tension force is a contact force. If you're not actually holding on to the thing, you can't stretch it. Magnetic force is non-contact. Magnets don't have to touch each other for you to feel the pull or the repel of them working on each other. Electrostatic force is non-contact. You don't actually have to have the electron touching a proton for it to be pulling it into the atom. And gravity is non-contact. If you are high up and you step off something, you don't have to be touching the earth for the Earth's gravitational field to pull you down. So we've got contact and non-contact forces there. So hopefully that makes things a little bit clearer as we get started. So I'm going to just see what you thought about those, or what you were, whether you were paying attention. Now, I'm going to be clear that the poll I'm about to launch has got a little bit of a trick to it. It's a bit of a trick question. See if you can spot it and see if you can do anything about it. Let's see. So here we go. Which of these, oh, I've spelt it wrong. Which of those is a non-contact force? Multiple choice. Let's see what you think now. Which of those is a non-contact force? Good. I can see people being a little bit unsure, and now I'm getting what I hoped for. Fantastic. Brilliant. That's really good. I can spot that a few people have spotted what you're able to do. And we are, like, no one has put push, which is wonderful, because someone put push the second I said it, because you definitely have to touch things. It's definitely a contact force. Very few people have written tension or click tension. That's good, because you have to have hold of it. And what I can see from the numbers I'm getting is that some of you spotted you were allowed to click more than one thing. You can click multiple answers, multiple choice. And the answers were magnetic, gravity, and electrostatic. You don't have to be touching anything for those forces to be able to act. Two magnets can pull each other without touching. The earth can pull you down even if you're not standing on it. And electrostatic, if you think about, instead of thinking about ions and electrons, if you rub a ruler or a balloon on your jumper and hold it over paper, that paper will stand on edge even if the balloon isn't touching it. So fantastic that you knew those. So let's talk about these resultant forces then. So that was just a little recap on forces generally. Okay. Now, this idea of a free body diagram is something I'm going to talk about. Free body diagrams is a phrase that comes up in your exams. And actually it just means when you draw an object and you draw arrows to show the direction of the forces. And recall types of forces. So we've looked at pushes and pulls and air resistance and gravity, and that we've got contact and non-contact. So now we need to have a look at what a resultant force is. Okay, so resultant forces are when you have got, like here, a force acting up and a force acting down. And we need to consider what the overall force is. is that square object going to move? Well, I can see that that arrow, which is the weight, and that arrow, which is the force of the table pushing up, are the same size. That means there is no resultant, because weight take away normal equals 0, because they're the same size. So that box is going nowhere. But we could make that a little bit different. Okay. When two objects push or pull on each other, they exert equal and opposite forces. So, like I said, you're sitting on your chair now, I hope. Or maybe you're sitting on the floor, maybe you're sitting on a sofa, but whatever you're sitting on or standing on is holding you up. And to hold you up, it has to be pushing back just as hard as gravity is pulling you down, because otherwise you would go straight through it. If it wasn't holding you up, you would just go down. So there is definitely a force holding you up right now. And we have to decide as to whether these two forces are going to make something happen or not. So here's an example. Okay, so here we've got a car. As you can see, it's a beautifully drawn, coloured in car. Those people that I teach will know that I didn't draw that because I can't draw. I'm rubbish at it. But here we've got the forces on a car. So there's the car, and we're going to assume it's moving forwards. So it's got a driving force, and that's the force from the engine, and that's going that way because that's the way the car is going. So if the car is going forwards to the left of my screen, that means air resistance is going to be trying to slow it down. And we all know that, because if you put your hand out of the window of a car, you can, don't, safety note, don't stick your hand out of the windows of cars. That can be very dangerous. But if you had ever done that in the past, you're never doing it again, but if you've done it in the past, you can feel the air pushing against your hand. There's the air resistance. And at the same time, friction, because we can hear, if you stand outside and you listen to cars go past on the road, you can hear their tires going around as well as their engines. And that's the friction of the road against the tires. So these three forces here are trying to stop the car. But this force here is making the car go forwards. Now, for the car to be going forwards, these forces must at least all be equal. If it's going at a constant speed, the forces must be equal, because otherwise air resistance and friction, if they were bigger, they would be slowing it down. If driving force was bigger, it would be speeding up. So they must be equal. And what we do is we add them all up. So let's say driving force was 50. If air resistance was then 30 and friction was 10 and 10, so we've got 50 going to the right and we've got 50 going to the left, which our resultant force then would be 0. The single final force that you find is called the resultant force. It's not always 0. Let's have a look at another one. So here's a rocket. I'm going to get you to do this one. So we've got a rocket, and the thrust, you can see this arrow is bigger. This is a free body diagram. A free body diagram is any diagram that's got arrows on to show the forces. So thrust is going up, and weight, which is the force of gravity, is pulling it down again. And we can see there that weight is half the size of thrust because that arrow is half the size. It's very important when you draw a free body diagram, the size of the arrows matters. So we've got 2,000 newtons going up, we've got 1,000 newtons going down. What is the resultant force? So I'm just going to give you a quick poll, and we're going to see what you think about that, having talked about what I have just said. So what is the resultant force on that rocket there? 2,000 up, 1,000 down. What is the overall? Now, what I should have put in there as well is I should have put a direction. I should have put a direction. So hopefully you're all shouting the direction at the screen to me. And this is looking really good because so far almost everybody has got this correct, and it's going very well. I've got 2,000 up, 1,000 down. What's the overall? What's the overall? Now, this is going very well because we've mostly got right answers here, and we're taking 30 seconds, and I'm aware you've got some adding up to do, so I'm going to give you a little bit longer. Brilliant. If you're thinking about having a last-ditch guess, do it now because I'm going to end it. Fantastic. So most people said 1,000 newtons, and that's correct because we've got 2,000 up and 1,000 down, so they are in opposite directions. So we take our 1,000 from our 2,000, and that leaves 1,000. And it's 1,000 up. That rocket's going to accelerate because up was the bigger arrow. I can see why people said 3,000 because they've added them together, and that also makes sense. But if the arrows are going away from each other or at each other, then you have to take the forces away from each other. The only time you add them up is if the arrows are both in the same direction. So if you had 2 arrows going up, you would add them up. If you had 2 arrows coming down, you add them up. If the arrows go away from each other or towards each other, you take them away from each other. Okay, so let's see how we do with perhaps another one of those. Let's have a look. Yeah, so here's another one. So we're going to work this one out a different way. Okay, so in this one, the rocket, which has a resultant force of 1,000, you just worked that one out already. You said it had 1,000. It hits a wall. So here's our rocket going, and it hits a wall and it stops. So if the rocket is going forward with 1,000 and it doesn't break the wall and it doesn't break the rocket, it just stops and falls. How big does the force on the wall, how big does the force from the wall have to be to stop the rocket? Have a little think about that.
Mr. Lamb, just while they're thinking about that, we just had a question. I've also just realised it says that my name is Mr. Lamb, which is very confusing.
Yeah, no, that is interesting.
We have a question. What if the arrows go diagonally rather than up or down or left or right?
Wow. Fantastic. I think that that's really rather a wonderful question, and I can possibly even guess who asked it. Now, when they go in year 8 and in year 9, they're very unlikely. Well, not very unlikely. No one will ever give you 2 arrows that aren't going both in the same direction or directly opposite to each other. When they are at an angle to each other, we do something called resolving the forces, and we either use trigonometry or we from that. That is something that you have to be able to do if you're doing the higher tier paper or you do triple science, probably by the time you get to the end of year 10. So it's a really good question, but I'm not going to teach you how to do it now. If you are an LTO and you ask that question, if you email me, I will send you some questions that you can try on that. It's a really good question. Right, I am going to end that poll now because we've got some interesting numbers. Now, the majority of you, but not everyone, said it would be 1,000, and that's absolutely correct. Because if we want it to stop, we have to have a resultant force of 0. Things that aren't moving have a resultant force of 0, and things that are going at a constant speed have a resultant force of 0. The only time the resultant force isn't 0, something's happening. It's either getting faster, it's stopping, or it's starting to move. So 1,000 and 1,000 come to 0, rocket stops. I can see why people said 2,000 again, and I can also see why people said 0 newtons. That's a really good answer, actually, because the resultant force is 0 newtons, and perhaps that's what you thought we were talking about there. So there's a couple of examples of that. So let's talk about some other things. So here's your task. This is a task that you are going to have to do on these when your teacher puts these in your classroom. So let me see if I can get this to work. Right. I'm going to try. So the first thing you're going to have to do is you're going to have to draw a car. Now, you don't have to draw a car. You can actually use that one there if you want. If you'd rather draw one and make it neater and take a picture of it or do it on Google Slides, fine. But I could use this card here. And then what you're going to do is you're going to have to put on all of the arrows that are here. So I've got a car of weight 5,000 newtons. Okay, so I'm going to put weight on. So I'm giving you a clue here. Here is weight. There you go. I'm putting an arrow on. And if that arrow is 5,000 newtons, you have to remember everything has to be to scale. So if I'm then going to draw a driving force of 2,000 newtons, that has to be just less than half the size of that arrow because they must be in proportion. It's really, really important. So driving force is forwards. So I'm going to put this arrow here, and I would measure it if I was handing this in, but I think that's about just under half the size. And I would label these arrows. So I would write 5,000 and I would write 2,000. So I'm going to then, your task is to then add all of the correct arrows with the sizes and to try and work out what the resultant force is up and down okay? There is a resultant force overall up and down, and there is a resultant force overall backwards and forwards. So we've got horizontal and we've got vertical, okay? And I want you to work out what those are. Having drawn the arrows on first, it's much, much easier if you draw the arrows first. Now, you will be very pleased that I'm not going to draw any more, those of you who have seen me draw before. So, resultant forces. We've got contact and non-contact forces. Contact forces, the two things have to be touching. Friction is an example, pushes are examples, tension is an example. Non-contact forces, no contact. Magnetic, gravitational are really good examples. Electrostatic are really good examples of that. We measure forces in newtons, given the symbol capital N. When we're looking...
Sorry, Mr. Lamb, can I just interrupt for a second? A question, would the arrow have to be facing the car in a diagram? So this is about the direction of the arrows.
Right. The arrow has to be pointing in the correct direction for that force. So for example, driving force must be making the car go forwards. So the arrow must point from the car to forwards. It can be behind the car pointing forwards, but what we normally do with forces is put them from the object in the direction they go. So driving force goes forwards. So my arrow, very deliberately, my driving force would go like that. Weight is a downwards force. Weight is what pulls us down. So I would be drawing my weight like that. But it experiences friction from the ground. Friction is trying to slow my car down. So it goes in the opposite direction to the car's movement. And so you need to look at the force and think, what direction does it go in? That is part of the task here, to decide what direction that force is going in before you add them up or subtract them from each other. And if you want to remember how to do that, you might need to play this video back. Arrows going in the same direction get added to each other. Arrows in opposite directions, doesn't matter whether it's outwards or inwards, get taken away from each other. And then you have to work out what's left and which way it goes. You might have to play this back to have a little think about that. So we were talking about forces, and I talked about contact and non-contact and newtons, and we were then talking about resultant forces. So if something is accelerating or decelerating, there must be a resultant force on it. Things with no resultant force stay still or keep going at a constant speed. And to find out the resultant force, we add or subtract all of the forces acting together and see what number we're left with. And then we have to decide what direction it goes in. And we do that by looking at all of those forces. So the thing is, one of the forces here is air resistance. And so you can see this car here. Now this car wouldn't necessarily be particularly fast having a look at it. It looks probably a little bit like my car, although my car's not yellow. And it doesn't go particularly quickly. But we need to think about, when we design things, we think about these forces. And we think about making our resultant forces as big as we can in the direction that we want our car to go. It makes them more efficient. It makes them more ecologically sound. You'll look at, if you look at electric cars, they work really hard to reduce their friction and their air resistance by being particular shapes and having particular shaped wheels, because it makes them more effective. So what do we call it when an object doesn't cause a lot of air resistance? Let's just have a little look at what you think or what you know about those words. Whoa, we're straight in with the right answers. Fantastic. This is looking really good. I've not read out the right answer, but quite a lot of you have answered already and got it correct. It's so far we're on 100%. This is going very nice. Excellent. It's still mostly all correct. That's 22 seconds. That's about half of you. I'm going to give it a little bit longer. I'm just watching the numbers going up. I'm not ignoring you. I'm seeing how many people are going to vote. So most of you have voted now. We're heading towards it having been up for a minute. So if you want a last ditch effort, you've got 5 seconds. I'm going to end the poll now. And the huge majority of you said streamlined, and that's exactly what we're talking about here. So streamlining, I'm going to go back in my videos a little bit. So streamlining is when we look at the contact force of air resistance. Air resistance is a contact force. If you don't have contact with the air, if you put it out of a car window, which you're not going to do, but if you put it out of a car window, unless the air particles hit your hand, there's no air resistance. That's what it is. It's air particles hitting you, trying to slow you down. Fortunately, they're not very heavy, so they don't. So this person falling is actually hitting air particles, and that is what is slowing them down. Okay, now that's a huge problem for design, for all sorts of design, cars, bicycles. The other force that we look at is friction. Now, friction only happens when two things touch each other. So the less surface there is for things to touch each other, the less friction we're going to get. Now, sometimes that's good, but sometimes that is a terrible problem, not having enough friction. So it's really important. So let's have a look at what we're talking about. For objects to reduce air resistance and upthrust in water, we make them streamlined. So boats are also streamlined to prevent quite as much resistance from the water. But look, there is also a time when we want to have high drag and frictional forces. So have a look at those 4 vehicles there, and you can see that they're really different in their shape. Now, I can hope that you can spot that 2 of them are very streamlined, and that's nice and easy, because what we're trying to do there is reduce air resistance to give us a bigger resultant force in the forward direction, because we've made the other arrow really small and we can go faster. So here is a bike with drop handlebars, which allows cyclists to bend down, put their head down and reduce their profile. This is a Bugatti for those of you that are car enthusiasts, and it is extremely carefully streamlined so that it slips through the air as quickly as it can, because that allows it to have a higher acceleration and a higher top speed. Over here, we've got things that are really chunky looking. We've got a big wheel bike. We've got a Jeep there with very large wheels. They have large tyres to increase the friction that they are able to apply to the ground to give them more grip. It's much better to have high friction if what you need is grip. You can see this with racing cars with huge wide tyres at the back, and all off-road vehicles and off-road bikes have chunkier tyres, because when we say more grip, what we mean is more friction, more ability to apply force to the ground to push us forwards. So all of those things in mind, here's your main task. You can do this in a variety of different ways. So let's have a look at it. This slide is for your answer. So I want you to explain about the difference between streamlining and friction and why they are advantageous for different things. But now we get on to a practical. Now, I'm not saying that you have to do this practical. In fact, I'm saying you really don't need to. However, if you fancy doing this practical, you can, because you don't actually need a measuring cylinder. You just need something that is reasonably tall and can have water in it. You can get things out of easily. That's really important. If you drop it in a bottle, you're going to be stuck here. But you don't need to do this practical. It's about designing it. You don't need plasticine either. Plasticine, blue tack, but you have to use the same, although there's 5 different shapes here, you're actually meant to use the same piece and make it into different shapes. If it's not the same piece, it's not a fair test, because you're also changing the mass as well as the shape. And what we're investigating here is shape. So you're going to design an experiment that would test your hypothesis. Now, your hypothesis in science, for those of you who can't remember, is your educated idea as to what is happening. I think when my shape is more square-like, it will fall more quickly. The reason for this is, I think that the shape that will fall the fastest is a sphere. The reason I think this is, okay, you've got to give an explanation. You've got to say what you think is going to happen and why. It might be that simple. Those of you who know who you are, who are working at a very high level, your hypothesis might have multiple strands to it. You might be able to rank order these objects and explain why they are in a rank order. What's also important is that you identify your variables. Now, I just talked about a control variable. You have to use the same mass of plasticine every time, because if you change it, you're not just changing shape, you're changing mass as well, and that's no good. There are other things you have to keep the same. You're going to have the same height of water every time. Okay, you're going to have some other things that I'm not going to mention. You also need to talk about your independent and your dependent variable. And if you can't remember which one's which, you might want to look up the song on YouTube, the variable song. And you're going to have to tell me what you are going to record and what you're going to change. Okay, so you're actually designing this practical. If you don't want to do it and record some results, that's extra. That's absolutely fine. Get a plastic bottle, cut the top off it as your measuring cylinder, find a lump of blue tack, put it in different shapes, drop it in, time it with your phone. Absolutely brilliant. Okay, you don't need to do that. I am not telling you that you have to do that. What I want handed in is the plan. So here's what the plan looks like. Now, there are a variety of different ways you can do this. If you find this idea really difficult, then you can use this slide to put your method on. And you do your method as a step-by-step method. So you would say, step 1, set up the equipment like in the diagram. Step 2, take the first shape, drop it from whatever height you've said you're going to drop it from, time it, do this 3 times, take a mean. We always do that, and we do it for a reason. I want to see if you can remember the reason. I would then do the next shape. Variables, you'd say, this is the variable I'm going to measure, this is the variable I am going to change, and this is the variable or the variables I'm going to keep the same. That's the easy version, that you write it straight on here. If you're better able to design an experiment and you've got the hang of this and you know that you've done it before and you've done it well, I want you to do the thing entirely however you would like. You might want to put a diagram in there. You're going to explain it step by step, but you're going to explain why you're controlling certain things, and you're going to explain what you mean by the variable you change and the variable that you'll measure, and you're going to tell me what variables they are. You're also going to draw a results table. It doesn't need results in it. It just needs to be able to record the results that you've told me you're going to take. So that's everything I want you to do with this week's. But remember, last week I said, in the last week before enrichment, which is next week, we are going to set you a Google form quiz. And the Google form quiz is going to be on everything that you've done in lockdown. So I gave you a practice one to do last week, which most people have handed in, and you'll get those back this week, but it will be longer than that one, and it will include everything that we've done. So the other thing I want you to do, if you saw my assembly, it was on revision. It was on retrieval practice, dual coding, and elaboration. If you haven't watched it, I want you to watch the recording of that, and I want you to use the retrieval practice bit to learn some facts about forces, about circuits, and about circuit symbols, so that you are able to answer questions about that on your Google quiz. So spend half your time on designing this investigation, and the other half your time on watching that assembly back and using the retrieval practice ideas to see what things you can remember for a Google quiz next week. The Google quiz, I'm going to say it again, I said it last week, will not be used for setting. It will not be used for targets. It is just for you to see how well you are able to use that retrieval practice idea to remember things that you've learnt yourself outside of the classroom. It will really guide you in being able to develop your revision technique, so that by the time you get further up in the school, you're so good at it that you can look at something and go, fine, I know how long it will take me to learn that. I'm going to go and revise. So thank you all for coming again. What I'm going to do now is stop recording